Good morning, everyone. My name is Rich Tansky. I'm our VP of Sales here at ChemMasters. We thank you for joining us this morning. Our webinar this morning is labeled as Concrete Defense, Prevent of Water, Corrosion, and Freeze-Thaw Damage. Very timely session for us folks up north entering the cold winter months. Our presentation this morning will run 45 minutes. And it will be followed by a 15-minute Q&A session. Just a reminder, your microphones are muted, so you'll need to submit questions through the chat box. We'll be reading those questions and then address them again after our 45-minute presentation. Your presenter this morning is John Fouth. John is our Vice President of Marketing and Business Development. John is very active in ACI. He is the incoming Director of Manufacturers Advisory Council at ASCC. Is a member of many of the ACI technical committees, including chair of ACI 515, the Protective Systems for Concrete. So everybody buckle in. John's getting ready to take us off.
Thank you, Rich, and thank you to everyone who's joining us this morning. Really appreciate your making the time. Hopefully this will be both informative and a little entertaining. As Rich mentioned, our title is Concrete Defense, Preventing Water, Corrosion, and Freeze-Thaw Damage, which are, very common modes of damage to concrete. They're not the only ones, but they are common enough that we're going to focus on those today. I'm going to start by identifying the problem. How does concrete deteriorate? Concrete by its nature is very porous. We've all heard it described as a big hard sponge. And that allows water and chloride intrusion, which we will find does damage to concrete in a number of different ways. It also is impacted by deicing chemicals that accelerate scaling and corrosion and other damage within concrete. There is, of course, in northern climates, freeze-thaw damage. And a lot of these contribute to rebar corrosion and carbonation and chloride ingress, which contributes to the rebar corrosion. And, these various methods or these various deleterious things, they impact concrete in a very bad way. And what we're trying to do is protect it from that occurring. Again, the porous nature of concrete allows water and chloride intrusion, rebar corrosion from carbonation and chloride ingress, freeze-thaw damage from saturated pore water, and de-icing chemicals that accelerate scaling and corrosion. So let's take a look at how each of these occurs and various strategies to prevent them. We've often heard, again, concrete being described as a big hard sponge. It's up to 40% void structure. So that porosity allows for easy intrusion of water and chlorides. Anybody that has any question about that, go take a bucket of water, go pour it on some unprotected concrete and see how quickly it absorbs. As water reaches the rebar level, that causes corrosion from carbonation and chlorides. Rebar and other structural steel has a passivity protection within concrete. The high pH of concrete, which tends to be about 12 to 13.5 as it's placed, that suppresses corrosion. And so for some period of time, concrete has a fair amount of protection just by virtue of that high pH. Unfortunately, carbonation reduces the pH of concrete, and that can occur over time. It does occur over time, and it can occur rather quickly in certain circumstances. When the carbonation reduces the pH below 10, that passivity protection is lost, and rebar can now corrode readily. What is carbonation? It's a good question. I'm not a chemist, but this is a pretty simple explanation. Carbonation is a chemical reaction between carbon dioxide and calcium hydroxide in hydrated cement paste. And that reaction forms calcium carbonate, which is the carbonation that occurs and lowers the pH of concrete from about 12 to 13 and a half down towards neutral. And again, the kind of the magic number is 10. As the pH drops below 10, that passivity protection of rebar is lost, and corrosion can occur. Here's kind of a visual representation. As concrete is exposed to water repeatedly, water dissolves CO2, which is naturally present in the air, and it forms carbonic acid, and that more rapidly reacts more rapidly with alkaline components in the concrete paste. And as that works its way down through the cover layer of concrete, it reduces the pH as it goes, and eventually it reaches that rebar level and eliminates that passivity protection that is inherent to the high pH of concrete. As we all know and have heard many times, concrete is very strong in terms of compressive strength. And oftentimes we get kind of focused on compressive strength. But most of the damage that occurs to concrete is because it is relatively weak in tensile strength. So that ability to pull itself apart. If you consider an average, mixed design that might have a 4,000 psi compressive strength, that means its tensile strength is only around 400 psi, which is considerably less. And as the expansion of corroding rebar occurs, and the expansion of water as it freezes, it imparts those tensile forces on concrete, and that's where our damage is done. So water reaching that rebar level time and time again, and as the passivity protection is lost, the rebar will begin to corrode and expand up to 600% as that corrosion occurs. That's a lot of expansion. That's a lot of force, internal force and tensile force on that concrete. And concrete is not designed to handle that. And as anybody who's left a bottle of water or a bottle of alcoholic beverage in the freezer overnight by mistake, we know that tensile force is considerable when it comes to freeze-thaw damage. Even though it only expands 9%, the damage that occurs is significant. Again, anybody who's left something unattended in that freezer can attest to that fact. And then all of this is exacerbated by the use of de-icing chemicals. I understand. I mean, everybody understands that de-icing chemicals are a necessity, especially when it comes to safety. I'm not going to make my grandmother walk up an unsalted walkway to get into her house, and so I'm going to use de-icing chemicals. But we use them understanding that they are doing damage, and the damage that occurs is that they create artificial freeze-thaw cycles. So in some of these northern climates, we've had many years here in the northeastern Ohio area where the temperature dips below 32 in November and doesn't get above 32 until March. And that's one freeze-thaw cycle. So, it's not, in terms of its impact on concrete, that's not that significant. The problem is we are using these de-icing chemicals over and over again maybe even several times a day. And those are all artificial freeze thaw cycles. And they are, in addition to the freeze thaw cycle itself, we're adding chlorides that accelerate the carbonation of the concrete and the corrosion of the rebar. So while they are a necessity in many areas and in many circumstances, we understand that de-icing chemicals are doing damage. You may also be able to recall the damage that's done on your own driveway or in your garage as your car comes in and carries the de-icing chemicals from the road. Oftentimes, damage is in two strips up your driveway, which is where your tires track. And in your garage, the damage is done at 4 points, where the four tires sit, and the ice that has accumulated alongside the wheel wells melts and attacks the concrete in that area. So it can be very localized like that, where the impact of de-icing chemicals is seen only in those areas that are actually being exposed to them. Water enables chemical reactions that break down concrete paste in other ways as well. They will dissolve alkalis in calcium hydroxide, making them available for reaction with dissolved CO2. The moisture that supports this ion mobility or mineral leaching allows the reaction front to move deeper into the concrete mix. In other words, these components of concrete paste are being dissolved and migrate out of the concrete paste. And the repeated wet drying cycles, whether it's rain, condensation, or groundwater wicking, is especially aggressive. The wet phase promotes the dissolution and reaction, and the dry phase draws in more CO2 through the pore structure from the surface. So this repeated wet dry is doing damage in and of itself. Here's an example of visual depiction as water migrates through the concrete slab. These minerals are leached out, and we are reducing the strength and the durability of the concrete as that occurs. So as a summary, water enables chemical reactions that break down paste and cause carbonation. Chlorides reduce passivity, the protection of the rebar due to the high pH in freshly poured concrete. Rust occupies more space, more volume, and that causes cracking and spalling due to its expansion within the slab. Freezing water also occupies more volume, more space, and that causes cracking and spalling within the concrete and oftentimes right at the surface. What are the strategies that we can use to protect against some of this damage from this damage occurring? And strategy one we're going to look at here is the protection of existing concrete. So this is concrete that is, as it said, it's already existing. It's over 30 days old. In many cases, of course, it's years or decades old. And that strategy is going to be different from a strategy that might be employed for freshly poured concrete. For existing concrete, the use of reactive penetrating silanes or siloxane water repellents is ideal. And its small molecular size allows it to penetrate deeply into that concrete surface and substrate. It chemically bonds within the pore walls for a hydrophobic barrier. And as the illustration exhibits, because of the hydrophobicity, boy, it's a little early for me to pronounce the tough words. That water droplet is not able to penetrate, and therefore we avoid the damage that might be associated with freeze thaw or from carbonation. Now, these materials react only in existing concrete, so they are not a good option for freshly poured concrete. Oftentimes, we try to think about what are the differences between silanes and siloxanes. They're kind of kissing cousins. And although I don't think that there is really a bad application for either of them, provided it's going on a cementitious material, they do have some subtle differences that might make a choice preferable for one situation or another. So we'll start with the molecular size. Silane is a very small molecule, and it is ideal for use where you're looking for penetration on dense concrete. So parking decks, bridges, garage floors, anything that is highly troweled, smooth troweled, hard troweled, where penetration would be difficult for a larger molecule. Siloxanes, a little larger molecule. It's more well suited for porous substrates. It's also well suited for substrates that might not be cementitious, such as brick. And so, therefore, it is oftentimes a preferable material for use on a vertical building exterior or home exterior. Brick, block, stucco, lightweight concrete. In this case, the larger molecular size can be used advantageously as well, because some of these types of structures have much larger pore structure, much larger capillary structure. You think of a split face block and how porous that is. And so the siloxane, the larger molecular size of the siloxane helps with making sure you're penetrating and coating the entirety of that capillary. The depth of penetration, silane again is going to penetrate more deeply in these dense, low porosity concretes, whereas siloxanes, although they do a fine job, they're not going to penetrate quite as successfully on those dense surfaces. But they do a fine job there, and they can be used in more readily in high porosity applications. Water repellency. Silanes have great long-term water repellency once they're reacted. The siloxanes typically a little shorter lifespan, but they are already partially reacted molecules, which is one of the reasons that it's allowed to be or can be used on substrates such as brick that are not cementitious. And frankly, I like the fact that they can be used a little more. I'm going to say I would prefer to put these in the hands of a homeowner, as an example, more so than I would a silane. Durability. Both of these materials are penetrating materials, so they are typically, durability is not so much of an issue, not in the way that we usually think of them from abrasion and surface contamination. They reside below the concrete surface, and they do their work within the concrete. So they're both highly durable products, especially when compared to film forming materials. Appearance-wise, both of them being penetrating products really don't change the appearance of the substrate surface. That can be a very important characteristic depending on the expectations of the owner. And so many folks do not want to see their concrete change in color and appearance. It also doesn't add anything to the surface, so it doesn't change the profile of the surface either. A film forming product will tend to change that surface. It could be any loss of profile on a surface does increase the chances for slip and fall, whereas a penetrating product leaves the profile of that surface unchanged. And each of them has their own limitations. The small molecular size of the silane may make it less effective on porous substrates. And siloxane is less effective on dense substrates. So, although these materials both perform very well, you may have some subtle differences from project to project or application to application where you may favor one over the other. I like to think of it as, there's a difference between you can't make a bad choice here. ChemMasters has several different options when it comes to penetrating reactive silanes and siloxanes. In water-based silanes, we have our PowerSeal 40, which is a 40% water-based material. It is low VOC in all states. Our PowerSeal 20 is a 20% solids reactive silane. It is also low VOC. You might choose the PowerSeal 20 on residential applications and maybe some commercial. The PowerSeal 40 is approved on many DOT qualified products lists. It is definitely more of a commercial and DOT product. On a solvent-based side, we have our Aquanil Plus 100 and Certivex Penseal 244 100%. Both of these are 100% active solid silanes. They are low VOC, VOC compliant in every state. Excuse me. We also offer our Aquanil Plus 40 and 40A. These are 40% solid materials or 40% active solid materials. The 40 is a high VOC product, and the 40A is a low VOC product. Why would I choose one over the other? I think at the end of the day, when you consider application rates, they are both very similar in terms of results. You could make a case that shipping a 100% reactive solids material is preferable to shipping material that has 60% solvent that is going to evaporate into the atmosphere. And so, you might favor the 100% over the 40 for that reason. You might favor the 40% over the 100 because, obviously 40% active is less expensive. So 6 of one, half dozen of the other. And then the Certivex Penseal 244 40% AIM is also a 40% active solids low VOC solvent-based material. And our water-based silane is our PowerSeal SS Plus. And that is oftentimes preferred for use on building exteriors, especially where you may have a variety of substrate types, brick, block, cement-based architectural stone, that sort of thing. So the key takeaways, silane is a very small molecule, deeper penetration, excellent water repellency, preferred for denser surfaces. Siloxane, little larger molecule, little shallower depth of penetration on dense concrete, very good water repellency, maybe preferred on more porous substrates. And again, here are some of the key differences. We've covered several of them previously. Dense substrates for silanes, more porous substrates for siloxanes, a little different depth of penetration, particularly when it comes to dense substrates. The silanes have the smaller molecule, which will penetrate deeper. Applications, which are these products best for? Silanes, bridge decks, parking structures, highways. And these are areas where, of course, they are very dense concrete design, mixed designs and finishes. Um, and there are also applications where you might be more concerned about chloride intrusion and freeze-thaw cycles because of the nature of the environment that they're in. Siloxanes may be best for vertical walls, building facades, masonry units, where the key is really water repellency and good surface protection. Um, Performance focus, silanes, long-term durability, chloride resistance, corrosion mitigation, siloxane, surface water repellency, and reduction of efflorescence. The substrate types, again, percent solids. It's not easy to compare these materials by virtue of their percent solids because of the longer and larger molecular size of the siloxane. But you're typically going to see silanes that range from 20 to 40% active solids, and typically siloxanes are in the 5 to 10% area. And of course, sometimes the cost may come into things. Silanes are higher cost. They do have an extended surface life in those critical applications, such as bridge decks and parking structures, whereas the siloxanes are lower cost, but have preferred characteristics in the architectural and building envelope applications. Again, these products do not change the substrate appearance. They're highly breathable. They do not have a film forming component. Therefore, they allow any excess moisture in the concrete to escape readily. Enhanced resistance to freeze-thaw cycling and scaling, superior protection for the rebar, and depending on the application, whether it's vertical, horizontal, whether it sees traffic, whether it sees de-icing chemicals, you could see service lives of 5 to 10 years or so. And as you can see particularly with the picture on the right, that is a saw cut with a water, obviously a drop of water on top, and you can see how effective they are at keeping water out of concrete, even when there's a substantial, means of ingress, which is that saw cut. Our second strategy that we're going to look at is for protection of freshly placed concrete, which is an entirely different situation. Our one-step film forming cures with integral reactive penetrating silanes or siloxanes. So one step in that you're getting both a film forming cure and a reactive penetrating silane or siloxane all in one product. It cures concrete. They cure concrete to ASTM C309 specifications. They provide your penetrating reactive silane or siloxane, and they are highly effective, very fast in terms of the impact on the project, and they are far less expensive than the traditional means of curing concrete and then going back and applying a reactive penetrating silane or siloxane. Let's take a look at that. This is the typical process, the traditional process for accomplishing both a cure and applying a penetrating sealer. Cure concrete for 28 days. By virtue of whatever method you might select that meets ASTM C309. You got to come back later and remove the curing compound or remove the curing method. You have to prepare the surface to receive the penetrating sealer. You have to apply that penetrating sealer. and then you have to get a little time for it to react and to cure out. This is a 30-day process if you do it by the book. It can be longer depending on the particular situation that you find yourself in. And you compare that with the application of a one step where you put it on apply it within an hour or two of final finish and walk away, and everything's done. It will cure the concrete, it provides the penetrating sealer, and all in one easy step, one and done. That's a stark comparison uh, for time and money. One application versus 30 days, and one step versus three steps, and the corresponding uh, labor costs that are associated with those three steps. It is a significant savings in time and money. How do these products work? Well, at the time of application, the silane molecules are drawn to the high pH of the concrete, and they are going to penetrate into the capillary pore walls, and while the acrylic membrane resides on the surface. So it's really simple. Um, we utilize the pH of the concrete to our advantage to accomplish this, and it is a one-step product giving you both ASTM C309 curing functionality, as well as, depending on the product that you choose, a penetrating reactive silane or siloxane that meets most state requirements for NCHRP 244 Series 2 and Series 4. Our one-step products exceed the curing requirements of ASTM C309 fairly significantly. They are the far better cures than just the minimum, and that is depicted here. Our one-step cure options, curing and sealing options, are our Silent Cure SRT, which is a water-based product. It is low VOC. It meets some states' NCHRP 244 requirements. It can be used on broom finish, smooth, troweled, and decorative concrete. And it's often used for residential and commercial applications. This is not a DOT product. I wouldn't recommend it necessarily for a DOT application, but for residential and commercial applications, this is a very forgiving and very effective product for both curing concrete and long-term penetrating silane siloxane protection. Our Silent Cure DOT is also a water-based product. It is low VOC. It meets NCHRP 244 requirements in most states. In fact, I'm not really familiar with a state that doesn't that it wouldn't meet. It is on many state DOT qualified products lists, and able to be used. Excuse me. And it is a water-based wax, white wax. So any place that a DOT might be using a white wax highway curing compound, and then wanting to come back and put on a penetrating silane, they can have the benefits of a one-step application as well, and all those benefits in terms of cost and time. It is also in DOT applications a benefit for safety because it is a one-step versus a three-step process. That reduces the amount of time and frequency that DOT laborers are exposed to traffic. And it is well known that restricted traffic situations are more dangerous than typical roadways. And so the fewer times that you expose contractors to restricted lane use and things like that, the fewer times you're exposing them to the potential for harm. Um, Silent Cure A is our low VOC solvent-based material. It is designed for broom finished and DOT applications. And it can be used in residential, commercial, and DOT. I typically see this used primarily in commercial and DOT applications. And then Silent Cure is our high VOC product in states that still follow the federal VOC regulations. And again, broom finished in DOT applications and primarily commercial and DOT applications. So oftentimes we get the question, how do penetrating sealers perform and compare to our one-step products? And so here are some metrics that you might consider when you're making those kinds of comparisons or decisions. Obviously, penetrating sealers do not perform a curing function, and so the one-step products are infinitely preferable in applications where you're going to need to cure freshly placed concrete. By virtue of the fact that you have a film-forming component that reacts or cures more quickly than the reaction that takes place with a penetrating silane or siloxane, they do provide better early protection for concrete. They have very similar performance characteristics when it comes to water and chloride repellency and freeze-thaw durability. I think both of them are extremely user-friendly. Obviously, anytime you take a three-step process and turn it into a one-step process, that is certainly making it more user-friendly than that traditional 30-day three-step process for curing concrete and then removing it and applying a penetrating sealer. And as far as longevity is concerned, I think you could make the case that penetrating sealers last a tad longer than our one-step options, but it's not significant. And certainly if you have to cure concrete, the advantages of one-step products versus penetrating products are significantly better. So strategy number 3, let's take into account a decorative component to the process. So prior to this point, we've been talking about protecting concrete in general, but there are unique concerns and characteristics associated with protection of decorative concrete, and that is primarily the aesthetics. You can have extremely well protected concrete, and if it doesn't look good, the owner is likely not to be very satisfied, and that puts contractors in a difficult position. How do I get this combination protection of and decorative appearance in a single product? And Chem Masters has an answer for that. So our decorative one-step products are high gloss. They deepen and enrich the natural colors that are inherent to concrete or to decorative concrete elements such as stamped concrete, exposed aggregate, things of that nature. It combines the curing membrane with the penetrating water repellent. It cures concrete, depending on the product selected, to both ASTM C309 and ASTM C1315 specifications. So the higher specified moisture retention of ASTM C1315. And our one-step products, decorative products, they are, again, both provide a cure and a penetrating silane. These products can be used on both existing concrete and freshly placed concrete. No restrictions. And they have the elements that people are going to be looking for, which is in decorative applications primarily. I want that protection, but I want the aesthetic qualities that are associated with decorative concrete. Our Certivex Guard Clear, a solvent-based product. It is not low VOC, so it's for the federal states or states adhering to the federal regulations. Broom finish, decorative finishes, pavers, residential, commercial, and its sibling is the Guard Clear AIM, which is low VOC. And again, these have have that film forming decorative acrylic component that makes that gives you the aesthetic qualities that are necessary for decorative concrete and pavers. So we want to when we're using reactive penetrating sealers, we want to apply to a clean, dry surface. Apply to a cured concrete. Recommended 28 days, but 14 days is a minimum. Our one-step products you can apply immediately after the bleed water is evaporated, within an hour or two of final finish. As soon as you get that final finish on, particularly with type 1L cement or concrete produced with type 1L cement, where we're worried about that early desiccation at the surface. Get it on as soon as possible. Comply with the cure rates. Don't over apply. I think that's something you hear about with anything that is particularly a decorative product. More is not better. More creates problems of its own, and we don't want to get into those. So overview, silane siloxane chemistries provide a proven long-term protection. Use of our one-step products can help with the project timing, improve meeting customer expectations, and still meet the long-term protection expectations. Our one-step products combine the benefits of both cures and reactive penetrating sealers. They save time and money, and I'm not aware of anybody that's opposed to saving some time and money. Here are some resources for you. ACI 308, which is 0.1-23, external curing of cast in place concrete. That's a specification. 308-16, the guide to external curing of concrete. 515.2-24, which is the selecting protective treatments for concrete guide, and 515.3-20, which is the guide for assessment and surface preparation for application of protection systems for concrete. We've got to shorten that name. That's a mouthful. So that concludes my presentation portion of today, and hopefully there are some questions that I can answer. And Rich, if you have accumulated some of those you might share on behalf of the group, I'd be appreciative.
John, thank you very much. Very informative. We do have a few questions. One of the first questions came out was, what can be done to reduce the concrete's void structure? When you had the slide on talking about voids, the question came in as far as what can be done to, again, reduce the voids in concrete.
Well, first of all, you have to separate out voids that are intended and that you want versus voids that are just kind of an unfortunate necessity. So you've got air, especially I'm going to limit my response to exterior concrete, because in interior concrete you don't have air entrainment. So in exterior concrete, you want air in your concrete. You want it in the form of small and large bubbles. Those bubbles serve a purpose for freeze thaw protection. It gives some place for the growing ice crystals to migrate to without doing damage and imparting those tensile forces. Um, so that air you want. Uh, then you have air that is, capillary air from water that is not consumed during the hydration process. Um, and there are less water means fewer capillaries. So water to cement ratio or water to cementitious materials ratio does play a part in that. Um, but you do not want to densify exterior concrete in the same way that you would in interior concrete. That would create a problem, a host of problems. So air is in concrete intentionally, um, and it does good. And then air is in concrete kind of out of necessity. That water of convenience, that the excess water that is bleed water, that water that isn't consumed during the hydration, the chemical reaction by how cement reacts to form concrete. That water, keeping it to a minimum reduces the unnecessary void structure.
One of the applications that seems always to be a challenge, and we have a lot of questions for, are residential garage floors. John, is there anything you would recommend for that type of application?
Yeah, I mean, it depends on what again, the customer expectations are. I'll use my own garage floor as an example. Um, First of all, I cured it when it was placed. I also cured my basement floor. My builder thought I was crazy, but I have no dusting concrete in my basement, which is great because it was cured properly, and I didn't have to worry about the surface dusting because it wasn't properly hydrated. Um, so if the expectations are to protect that floor without consideration for aesthetics, a penetrating silane, that's a dense surface. Most of them are, highly burnished and high troweled surfaces. So something along the lines of the Power Seal 20 and the Power Seal 40 would make for good choices to protect it from the road salts that are being brought in on the tires during the in the wheel wells during the winter months.
What are your thoughts on using a silicate on exterior concrete for protection?
Well, again, silicates are densifier hardeners, and um, uh, they have their place in the industry. All chemistries do. I like to say there are really no bad chemistries. There are just bad applications for them. Um, so if I'm densifying and hardening a thin crust at the surface of exterior concrete, first of all, I'd be concerned that I'm taking that protective air entrainment out of there. It's the same reason you don't hard steel trowel exterior concrete because you end up with basically the same results. A thin surface that is highly densified doesn't have air entrainment protection. Um, you also have the added disadvantage of exterior concrete does not have a vapor barrier beneath it, whereas interior concrete does. And as moisture is always coming up through through that concrete, it would normally go into the atmosphere. It's drawn to the warmth of the sun, or even just the warmth of the day, um, since moisture is drawn to heat. And if it starts to condense underneath this thin densified layer, and you go through a freeze thaw cycle, you could lose, the entire surface of your concrete, delamination. I know in Northeast Ohio we had some issues several years ago. There were a lot of driveways that were being, um, quote, cured with densifiers, and a lot of surfaces were lost. And I know because I was brought in to offer some advice there, and it's the wrong application in exterior concrete for a silicate, surface applied silicate, just to be specific.
Kind of going along the same lines, we had a question come in that asked, when using silent cure SRT, do you see maybe using that as a curing compound followed by an application of a densifier on a garage floor?
Well, if I were to want to do the two of them, I'd probably do them in reverse. The densifier wouldn't be able to penetrate the film forming component of the silent cure SRT. So I would prefer to densify first and then go back and put on the silent cure SRT. Now, you know, uh, whether you could do that and get the SRT on at an appropriate time to maximize its curing benefits, I guess that might be subject to some question. And I'd also, kind of state that, the hard troweling that occurs in a garage floor, it's doing the job of densifying and hardening that. And that's the whole purpose of it. So I'd question the need for a densifier in that application. Not saying don't do it. I'm just saying I question it.
Right. I think the last question we have is, um, finishing aids have become popular. If you're using a finishing aid, does that create any problems with using a silane or siloxane on your concrete?
Um, First of all, finishing aids we have no data to suggest that it would create a problem if there's an incompatibility. Um, but I would also mention, that a finishing aid is being used when something is on mostly, decorative type applications or applications where it's going to be troweled. I'm not really sure that finishing aids are being used on, and somebody could correct me if I'm wrong. I'm just not familiar with it on, your broom finished concrete and things of that nature. Um, but they certainly, I guess, could be. Um, but we're not aware of any incompatibility between those.
Gotcha. I had one more question come in. Um, I think you kind of answered before on life expectancy, but with your silanes and siloxanes, how often would you reapply?
Well, I would reapply when it's needed, and that's kind of a silly answer, but I hate wasting money myself. So I would check to see what is the absorptivity of the concrete before I decided to reapply. I wouldn't assign a number to it. Oh, in 4 years, in 6 years. Um, so if you take a little bit of vinegar, a capful of vinegar out to your concrete, and you pour it on the concrete, and you are a little patient and wait to see if it bubbles, that's going to tell you whether or not you've got a lot of absorptivity. Just taking some water out and pouring it and seeing if it is just wetting out the surface or if it's actually absorbing, that's going to tell you whether or not absorptivity is occurring, and you've got the need perhaps for reapplication. Just in general, 4 to 6 years. 4 on really harsh environments, and maybe 6 or 7 years in southern climates where they see no freeze thaw and they see no uh, uh, de-icing chemicals, but they still want to protect against carbonation and corrosion of rebar. That might be, and maybe it can be as much as 10 years. I mean, there is data out there to suggest that it can be as much as 10 years for protection of concrete with silings.
Thank you. John, thank you very much. Very informative this morning. I know it's hard to get all that information into the time frame that we have, but I thought you did a tremendous job. We thank everybody for attending this morning, and we'll leave you with the reminder that this webinar will be posted online, and you will be able to access this probably sometime next week. Again, thank you very much for attending.